Hello everyone, we are Group 1. Today we are going to deliver our lecture on the CIV1171 seismic term project. Here's the outline for our presentation. Firstly, we will go through the project statement and briefly summarize the procedure and results for our preliminary design. Then we will go through our detailed design after we analyze the model in etaps. Finally, we will evaluate the nonlinear behavior for our structure in the assessment report part and compare the results. Our design building is an 8-story steel structure located in Vancouver, BC. The office is 32.5 meters high and it utilizes a buckling restrained brace frame system in west-east direction and a moment-resisting frame in north-south direction to resist earthquake forces. The figure shows the plan view and the general view of the seismic force resisting systems. The soil condition at the site is classified as Type D, as per NBCC 2015. The peak ground acceleration and peak ground velocity are shown on the slides. The application factors are calculated accordingly. The table and the graph on the slides shows the design spectrum. In terms of the structural potential irregularities, as per NBCC, Type 1, 2, 7, and 9 type irregularity will require a more in-depth analysis after sizing the SFRS members. Here's the important design control parameters that are used to calculate the base shear in the seismic force resisting systems. RDR0 for BRBF frame and MRF are shown on the slides. As per MECC, the formula listed are used to calculate the floor shear and the upper and lower limit for the shear force. The base shear for the BRBF system is 9,008 kilonewtons, and the base shear for the MRF frame is 5,462 kilonewtons. By applying the equivalent static force procedure, the shear forces acting on each floor are given on the slides. Based on S16 design of steel structures, we pre-select our steel members to resist the calculated lateral and gravity load under a certain load combination for our preliminary steel design. The formula on the slides are used to calculate the story drifts, and the table shows the drift and percentage for each story. They all satisfy the 2.5% drift limitation. The SFRS steel tonnage are also calculated. 30 metric tons per frame for the BRBF and 217.4 metric tons per site for the MRF frames. After the preliminary design, Dimitri and Egli will deliver the process and results for the detailed design report. And these slides outline the purpose and the summary of the detailed report.
For our structural model, the software ETABS version 18 was utilized. We constructed a model of the full building structural system with all the main beams, secondary beams, columns, braces, as well as all the required loading provided to us in the project statement. Once the building was modeled and all restraints such as end moment releases on all simply supported elements were inputted into the model, an RSA analysis was conducted. This analysis was conducted by restraining the model in one axis and running the modal analysis. This provides us with a period, base shear, and displacement parameters for each direction x and y. Per code requirements, the base shear provided by ETABS in each direction after each RSA analysis were scaled down accordingly until convergence of the period and base shear were obtained in each axis. After obtaining all the necessary parameters after model convergence, the detailed design of each SFRS began.
I'm going to talk about the MRF system, and I'm going to start off by looking at this modal analysis. So you can see that even after only 2 modes, we are above the 90% mass in our building. Here we check the torsional irregularity based on the maximum average displacement. We did find that we have a vertical stiffness irregularity based on the first and fifth floor. Now The most important values that we got was the base shear of 5462, a period of 2.13 seconds, a drift of 0.3%, well under the 2.5 code limit, and we did incorporate very heavy sizes for both beams and columns. For the actual design, we looked at the beams as class 1 sections and the maximum plastic moment, and we checked the beams for the combined axial flexural strength. The columns were designed as a weak beam strong column connection, also class 1, and is also checked for the combined axial flexural strength. The drift limits were limited to 2.5, and the first story column was designed as a yielding element. For the beam design, the beams were checked for the reduced beam section, and the columns were checked for the web panel zone. The connection was done with bolted web and welded flange.
And here's the main design checks for the BRBF system.
Moving on to the BRBF. Once the RSA analysis was complete, the bracing members were designed to be able to withstand the story shear at each level. Once it was deemed not necessary to redesign the bracing members, the final RSA analysis was run and all necessary parameters were obtained. Here these parameters are illustrated. Final period of 1.319 seconds, design base shear of 10,057 kilonewtons, and a maximum drift percentage of 1.6%. Additionally, all irregularities were checked after each iteration, and our building was deemed to have vertical stiffness irregularities. Once the building was deemed to meet code requirements in terms of drift percentage, and the bracing members were designed to be the yielding members, design of beams, columns, and connections began. The beams, columns, and connections were designed as a capacity-protected elements, and the design forces for them were obtained from the probable compressive and tensile forces of the bracing members. To save time, I will not go over all of our member sizes, but for example, on level 7, the upper braces had an area of 1,550 millimeters squared, the lower braces were 2,700 millimeters squared, the beam was a W250 by 73, and the columns are W310 by 118s. Our typical connection included a 510 by 550 gusset plate with double-sided 8mm fillet welds on the beam and column, with 6 1.5-inch bolts connecting the gusset to the splice plates, and 6 1.5-inch bolts connecting the splice plates to the steel core. The probable foundation design forces obtained were CF equals 13,962 kilonewtons, TF equals 9,432 kilonewtons, and VF equals 2,386 kilonewtons. Forces for all capacity protected elements are illustrated here, including diaphragm and foundation forces.
The foundations were designed as capacity protected, so the forces were quite huge because we had to multiply earthquake forces by our DR naught 1.5 and 5. As you saw before, this is our final section sizes. And this leads me to my next slide, which shows that the steel tonnage for the MRF had a huge reduction because we chose deeper sections with lighter weights.
Thank you, Dimitri and Egli. Finally, Anas will deliver the key points for the performance assessment report.
I will be talking about the nonlinear time history analysis of our design building. The purpose of this type of analysis is to observe our structure's response to a real-life earthquake loading scenario. Foreground motions are provided in order to complete this analysis. This section will go through our modeling approach, the results, and our comparison with the detailed design. The previously built 3D model was converted into a 2D model in each direction. To incorporate the gravity loads of the overall building, a leaning column was modeled and connected to each SFRS with pinned rigid links. The rigid links were considered to allow the entire structure to move together. To consider P-delta effects, gravity loads were applied to the leaning column at each level, depending on the tributary area with respect to the entire structure. A 5% damping factor was included in our model. Finally, the nonlinear elements were defined in each SFRS system. For the BRBF, a multilinear plastic link was modeled in its axial direction. An isotropic hysteresis model was considered. The probable tension and compression values from CSA S1619 were used to define the link's nonlinear behavior. For the MRF plastic hinges, the nonlinear behavior was defined according to the stiffness requirements for a fully resistant moment frame and modeling parameters defined by the ASCE 41-17, Chapter 9. These are the key response parameters for the BRBF. The period was found to be 2.38 seconds. The The story drift data for each ground motion provided was analyzed and an average was taken. For the BRBF, an average drift of 0.007 millimeters per millimeter was calculated as a top story. After the earthquake has occurred, an average residual drift of 0.0012 millimeters per millimeter was calculated for the top story. Similarly, for the MRF, a period of 2.49 seconds was found according to the modal analysis, and the average drift of 0.017 and 0.0025 was calculated for the maximum story drift and the residual story drift respectively. Here you could see the hysteresis loop for the BRBF link on the 8th story and the MRF plastic hinge response on the 8th story due to ground motion 1. This is a key diagram to consider and analyze because it ensures that the yielding elements were modeled correctly and with no problems. Some things we looked for included the loading and unloading cycles and ensure our hysteresis was not pinched. This is our comparison between our performance assessment and our detailed design. We compared our drift values. For the BRBF, our values were much lower than our detailed design, which may indicate this, that our building may have been, our SFRS may have been over-designed. For the MRF, the drifts were within an acceptable range compared to the drifts calculated in the detailed design. The first challenge in this project was completing the time history analysis with ETABS. Obviously, the period for the BRBF did not match what was defined in the detailed design report. This may be due to the different ways the braces have been modeled in each design stage. After completing all the design stages for this project, the following conclusions can be made. The dynamic RSA analysis is important and can optimize our SFRS design and have an impact on the overall cost. The SFRS design under the nonlinear time history analysis meets the NBCC drift requirements in all directions. The nonlinear time history analysis results indicate that the structure may have been over-designed. And that takes us to the end of this presentation. Thank you very much for listening.